Continual learning on non-stationary streams is usually framed in terms of gradient descent, replay buffers, or parameter regularization. But for edge devices and real-time streaming, that paradigm is often too heavy. What if we could build a learner that is gradient-free, local, online, and completely append-only? The intuitive pitch is simple. If regimes recur, why relearn from scratch every time? You should just recognize what you already know and warm start. This paper makes that intuition mathematically precise, and more importantly, it draws exact boundaries around where it stops working. Let's formalize the setting. We're dealing with recurring regime streams. Imagine a sequence of blocks, each drawn from a fixed categorical distribution over a d-dimensional probability simplex. There are k distinct regimes, and they appear repeatedly across R blocks. The key parameter here is the separation, delta, defined as the minimum total variation distance between any two regime distributions. Total variation is just a standard metric for how different two probability distributions are. We also track recurrence density, which is the ratio of total blocks to unique regimes. Now compare two learners. First, a memoryless reestimator. It carries zero state between blocks. Every time a new block arrives, it throws away everything and reestimates the distribution from scratch. Second, a warm start library learner. It maintains a fixed-size library of stored prototypes. When a block arrives, it first recognizes which regime is active, then warms up its estimate from that prototype. If it's a genuinely novel regime, it appends a new prototype to the library and never edits it again. That last point is critical. Identity clean appends guarantee zero forgetting by construction. Here is where the math gets interesting. The memoryless learner pays the full estimation cost on every single block. Estimating a d-dimensional categorical distribution to within a target accuracy epsilon requires theta, d/epsilon2, samples. That's a fundamental minimax lower bound. So over R blocks, the memoryless cost scales as theta, rd/epsilon2. But the warm start learner decouples the problem. On a recurrence, it doesn't need to estimate from scratch. It only needs to recognize which of the k known regimes is currently active. And here's the breakthrough. Recognizing the active regime costs O log k/delta2 samples. Crucially, that term is completely independent of the dimension dy. Because you're no longer learning an unknown distribution. You're running a sequential multi-hypothesis test against a fixed library. The sample complexity is governed by the Chernoff information between the hypotheses, which scales with the log of the hypothesis class size and the inverse square of the separation delta. So you get a clean separation. Estimation costs theta d/epsilon2, recognition costs O log k/delta2. The advantage isn't just a constant factor. It scales linearly with dimension and recurrence density. The paper proves an amortized recovery cost separation. The warm start learner's total cost is bounded by k times the estimation cost for the first occurrences, plus r minus k times the recognition cost for all recurrences. That gives us O, kd/epsilon2 plus rk log k/delta2. Compared to the memoryless baseline, the gap is exactly r minus k times the difference between estimation and recognition. But this isn't just an upper bound. The authors prove both terms are minimaxed tight. The recognition bound matches a Fano information theoretic lower bound for sequential hypothesis testing, and the estimation bound matches the standard LeCam and a SWAD constructions over a packed simplex interior. So the decoupling is mathematically optimal. Now a fair objection immediately arises. Doesn't a classical Bayesian learner with a library, like a Bayesian Online Changepoint Detection model, or an online HMM with state birth, achieve the exact same cost structure? It does, and the authors are explicit about this. This paper does not claim to beat the Bayesian gold standard. It claims to tie it. The contribution is paradigm realization. You're getting the same amortized sample complexity frontier, but achieved through a gradient-free, append-only substrate with no end-to-end backpropagation, zero forgetting by construction, and no hyperparameters. The Bayesian baseline maintains full posterior variances and evaluates omega, k, transcendental functions per step for normalization and evidence updates. Transcendental functions are things like logarithms, exponentials, and gamma functions that are computationally expensive on edge hardware. The count-calibrated warm start learner evaluates zero transcendental functions per step. It just does count addition, an inner product argmax, and one division. On resource-constrained substrates, that arithmetic separation is operationally decisive, even if the sample rate ties. To make this tie sharper, the paper introduces a count-calibrated warm start. Instead of using a fixed pseudo-count prior, you store each prototype as its raw accumulated counts and total sample size. The warm start precision self-calibrates from the prototype's own count. On the first cold occurrence, you've already paid the estimation budget, so the stored counts are already within tolerance. On recurrence, you run the same sequential test, but now the stopping threshold and warm start precision are derived directly from the conjugate counts. The result is that the warm start learner matches the Bayesian baseline up to a bounded, never-negative overshoot of O log 1/p min/delta2 samples. That overshoot is exactly the walled overshoot from the hard count likelihood ratio test relative to the Bayesian soft posterior. It's hyperparameter-free, dimension-independent under interior support, and never surpasses the Bayesian baseline. Let's be explicit about where this breaks down. First, the number of recognizable regimes is capped by simplex packing. Simplex packing is the geometric limit on how many distinct distributions you can fit in D dimensions while keeping them separated. For a random Dirichlet model, the typical closest pair collapses past a random model wall around E theta, D. Even with optimal packing, you can only hold E theta, D regimes at constant separation. Second, the result is condition-gated. It assumes supplied block boundaries. If you remove that and require autonomous change detection, the paper proves an impossibility at the packing wall. Any sequential detector with a bounded false alarm rate must incur a detection delay that scales as 1/delta 2. When regimes pack tightly and delta approaches 0, that delay diverges. No fixed, adaptive, or Bayesian detector escapes this false alarm delay frontier. Third, the advantage vanishes entirely if regimes overlap. The recognition margin collapses, and you're back to full estimation costs. The theory is backed by 3 layers of empirical corroboration. First, a synthetic dimension sweep shows the decoupling in action. As D grows from 16 to 64, the memoryless cold re-estimation cost rises roughly 4-fold, tracking the theta D/epsilon2 term, while warm start recovery stays flat near its recognition floor. Second, the count-calibrated variant ties the conjugate Bayesian baseline on per occurrence recovery across a D times K times rho grid, with a bounded gap that matches the theoretical overshoot bound. Third, they test on real regime distributions using empirical K-mer laws from 4 genomes spanning 19 to 72% GC content. The dimension-dependent separation reproduces exactly. Memoryless cost scales linearly with D, while recognition stays dimension-independent. There's also a real sequential stream from a neuroscience task, but it sits in the D equals 1 corner, which is exactly where the theory predicts a near-null advantage. So what does this actually give us? It gives us a rigorously bounded, gradient-free architecture for continual learning on recurring streams. It proves that recognizing a known regime is fundamentally cheaper than estimating a new one, and that gap scales with dimension. It shows you can match the sample efficiency of classical Bayesian changepoint detection without backpropagation, without hyperparameter tuning, and without catastrophic forgetting. But it also draws a hard line. Autonomous detection fails when regimes pack too tightly, and the advantage disappears when separation vanishes. This isn't a silver bullet. It's a precise tool for a specific class of non-stationary streams, realized in a paradigm that prioritizes local updates, append-only stability, and transcendental-free arithmetic. If you're designing systems that need to recover quickly from recurring shifts without retraining from scratch, this cost structure is exactly the frontier you should be building toward.